So I've ummed and ahed a little bit about whether I should do an extra on this. And when I mean extra, it's not really extra, whether that could occur on your exam or not. And I'm thinking there's a couple of reasons why I'm going to do this. That it's kind of ambiguous. It says heat of combustion. So I am going to talk about that in detail. Maybe or maybe not more than what they say. But if they say analyze, just analyze data for this sort of stuff, they could give you a question that has all the data there and it requires understanding. It also says neutralization, heat of neutralization, which I don't actually list out specifically because it seems to be obvious if it's enthalpy. They're all the same thing. It's 1 mole of something at standard at a set temperature and pressure, how much heat is released. And it says reactions in aqueous solutions, which is quite vague, which could technically include enthalpy of solvation, solution, or hydration. And so I'm just going to go over that. It is also useful in that it does tie together atomic structure. These are actually enthalpies, ionization energy and electron affinity. It does tie in together, so that's periodic trends, atomic structure, and the strength of a lattice. So all of these combine together with Hess's law, which is ionic bonding. And it also helps you understand why and how it all turns together. We can actually do reactions, theoretical enthalpies, theoretical reactions, and chemical bonds that might not be possible. I'm going to go very quickly, but first of all, you need to know sort of like the definition of all of these different enthalpies if you're going to work out how to use the reaction properly. So for combustion, it's the various different chemicals combining with oxygen to produce products. And so sometimes it's reactants minus products, sometimes it's products minus reactants. But if you know what the thing is doing, that they're all going to this way, and then Hess's law means you keep this one as positive and you turn this one to be negative. So this one's reactants minus products, not products minus reactants. Okay, and that allows you to, you already can do bond enthalpies to work these out, but you can now use a table of combustion enthalpies. In a similar way, you could get a table of formations. So they're basically the elements forming compounds. So there'll be a list of compounds and how much it takes to form the elements. And so that's represented by this. And in so that case, it's going in the opposite direction. So you've got a list of chemicals and it's their enthalpies of formation. You need to know their elements going to those chemicals. And so in this case, the reactants is minus. Okay, so that's how you work out enthalpies for all of these, how to do the enthalpy calculations. You have to work out what the definition is. So which one's positive, which one's neg. And there's just some examples that you can pause on and look at. That's using an enthalpy of formation table. This one would be an enthalpy of combustion table, I'm assuming. Yes, because the water's gone, oxygen 0. Okay. Now just quickly over here, so there are enthalpies for everything. So enthalpy of solution is solid dissolving. If I can find my pen. Enthalpy of hydration is a gaseous going into water. Now, if it's not water, it's enthalpy of solvation. And then you've got lots of other enthalpies going from the standard state to a gaseous state. Ionization energy and electron affinity we've already covered. And then there's lattice enthalpy. This is the strength of an ionic bond, how much energy it takes to break up that solid into gaseous forms. Now, the power of Hess's law is that we can combine, if we can't actually, well, certainly can't in the lab get sodium chloride and turn it into chloride ions and sodium ions. That would be, I'm not quite sure if that's even possible, but certainly dangerous, as even chlorine or sodium would kill you, would blow up in your face or poison your lungs. In a high energy state would be even less likely. But we can do all the separate bits individually and add them up and work out what the actual energy is. So just quickly, if I just show you here. So we're grabbing the sodium to a gas, chlorine to a gas. We add or take ions from those things. God, that music next door. Anyway, and then we can just add them all up together in this state here to work out how much of how to get it all into the lattice or vice versa. Don't you want to overanalyze, that's going way too far, but just to appreciate there are some concepts there that could be helpful in an exam.